This is a problem sent to me by a student at I.S.U State wanting some help on some Riemann Sum problems. And he sent me this problem. It says, calculate the Riemann Sum. And we have this capital letter sigma here, which means to take the summation or to add up. And then it says to go from 1 to n, I equal 1 to n, f of x bar sub I times delta x sub I for the given data. F of x is x minus 5. So our function is x minus 5. P here is giving our partitions. So our first partition is going to go from 3 to 3.5, then 3.5 to 4.25, 4.25 to 5.5, 5.5 to 6, 6 to 7. Also given in the problem were our x bar sub i's. X bar sub 1 is 3, x bar sub 2 is 4, x bar sub 3 is 4.75, 6, 6.5. And we can find our f of x bar sub i's by plugging those numbers into the f of x function. So this function is fairly simple. It's just take x, subtract 5. So 3 minus 5 would be negative 2. 4 minus 5 would be negative 1. 4.7 minus 5 would be negative 0.25. 6 minus 5 is 1. 6.5 minus 5 is 1.5. And what a Riemann sum is really asking you to do is to look at a graph of your function, the graph of x minus 5, which I've graphed here. Now I haven't graphed the whole thing because my partitions only go from 3 to 7. So you can see I started at x equal 3 and I stopped at x equals 7. And you notice if you do 3 minus 5, you get negative 2. So I graph the point 3, negative 2. And you notice if you do 7 minus 5, you get 2. So I graph the point 7, 2. I know that x minus 5 is a linear equation, so I drew my straight line in. What we're going to look at is this area. And what we're going to do is look at the area for each partition. So the first partition goes from 3 to 3.5. So that would be this partition right here. The next partition goes from 3.5 to 4.25. So that would be this section of the graph right in here. And then 4.25 to 5.5. So that would be this area from 4.25 to 5.5. And then from 4.25 or 5.5 to 6 would be this partition. And from 6 to 7 would be this last partition. Now, you might be wondering, okay, if I'm doing a Riemann sum, that means I'm trying to add up the areas of rectangles. These don't look like rectangles. Well, you're going to use a rectangle, and that rectangle's height is going to be based on, you can see right here, we're going to take f of x sub I times delta x sub I. So, what that means is we're going to take the height of the rectangle, which could be positive or we could consider it negative when we go down, times the change in x sub I, change in x of 1, for example. So, for example, our first change in x, our delta x sub 1, would be 0.5. That can be seen on the graph that this is this partition right here from 3 to 3.5 at 0.5 units wide. Now to get the height, which is actually going to be a negative number here coming downward, f of x sub I, we're going to plug 0.5 into this f of x equation. So let me write it out a little bit better here. So what I'm doing to get this expression is I'm going to plug 1 in for I. So I'm going to have f of x bar sub 1 times delta x sub 1 plus, then I'm going to plug a 2 in. So I'm going to do f of x bar sub 2 times delta x sub 2 plus, then I'm going to plug a 3 in. F of x bar sub 3 times delta x sub 3. Remember, delta means change. We're looking at the change in x. Plus f of x bar sub 4 times delta x sub 4. Plus, and I'm running out of room here, got to do one more though. Notice there's going to be 5 changes in x, 5 partitions. 1, 2, 3, 4, 5. So I'm going to do one more. So plus f of x bar sub 5 times delta x sub 5. So let's go ahead and just calculate each of these and add them together, and we'll have our answer. So the first change in x, delta x sub 1, is 0.5. Put it on a little lower so I don't run into my work on the right side. And my first height would be what I get when I plug x bar sub 1, which is 3, into the f function. I get negative 2. So if f of x bar sub 1 is negative 2, plus, take your second change in x times f of x bar sub 2. F of x bar sub 2 is negative 1, right there. That's just saying that, maybe if I can give you a little bit better idea of what we're doing here. When we take negative 2 times 0.5, what we're really doing is estimating this area right here, this rectangle. That rectangle is 0.5 units wide, it's negative 2 in height, so we're going to get an area of negative 1. This area, and really it's not area, we're evaluating an integral. It's not really area, but because it's negative, but it's area that's below the x-axis, so we're going to use a negative there. F of x bar sub 2 is negative 1 times the second change in x. The second change in x goes from 3.5 to 4.25, so that would be 0.75. On the picture you can see it's 0.75 wide, and it'd be negative 1 tall. So that puts us at about right here. So the second answer is estimating that area. What did I say it was? 0.75. So the estimate on that area is negative 0.75. And areas can't really be negative, but we're estimating an integral. Integrals can be negative when they're below the x-axis. Plus f of x sub 3, which is negative 0.25, times the third change in x, delta x sub 3, which would be 1.25. If you take 5.5 minus 4.25, 1.25. So plus, if we multiply those, we could do it this way: 1/4 times 1 1/4 is 5/4, so it would be 5/16, right? 5/4 times 1/4 would be negative 5/16. Or we could figure out the decimal for that. Next, f of x bar sub 4, which is 1, times delta x sub 4. The fourth change in x would be right here. And it would be 6 minus 5.5 would be 0.5. So 1 times 0.5 comes out to 0.5. And so, negative 1 is estimating this area. Negative 0.75 is estimating this area. Negative 5/16 is estimating this area. Let's see, 1.25 wide. You can see that the function, in this section, the function is more below the x-axis than above, so it's going to have an average negative value of negative 0.25. So really what we just did is we found about this area right in here. And then we took 1 times 0.5. Whoops, let me finish that out. This is 0.5 wide, and it's an average, it's 1 high. So we just estimated that area as 0.5. Now we'll do our last area here, which is f of x sub 5, x bar sub 5, which is 1.5, meaning this isn't 1.5 high, times our last change in x, which would be 1. Delta x sub 5 is 1. So it's 1 unit wide, and we said 1.5 units high. Make sure I have that right. Yep. 1.5 times 1. 1 wide, 1.5 high would be about right there. So it'd picture, we're talking about that area right there, and that comes out to 1.5, right? 1.5 times 1 is 1.5. And remember, what we're doing with the Riemann sum is we're really trying to estimate, this area between the curve, in this case it's a straight line, and the x-axis. So we're really trying to estimate an integral. We're trying to estimate the integral of f of x dx, in this case going from 3 to 7. So we're trying to actually estimate this area, the area of these two triangles. Of course, this negative area would probably cancel out this positive area, so we really should get an answer of 0. The exact answer here would be 0, but using a Riemann sum, we would add these together and see what we get. So let's go ahead and do that. I'm going to go ahead and use a calculator to help me out here. Well, I can, -1 plus -0.75 would be -1.75. These two together would add up to 2. So -1.75 plus 2 is 0.25 minus 5/16. 0.25 minus 5 divided by 16 is -0.0625. Which is pretty close to 0, which would be the actual value of this integral. So using estimation, using a Riemann sum, we come up with this green answer, which is very close to what the actual value would be if we took the area of this triangle and subtracted it from this triangle. We would actually get 0.